Okay, notes 2, significant tests for means. So it says important ideas from confidence intervals for means. Okay, so it says proportions are used with categorical data. When you split your data into successes and failures, and means are used with quantitative data. Proportions, categorical, means, quantitative. When n is less than 30, we check for normality by graphing the sample data. And then it's important to note that we're not trying to prove that the sample data is normal, but instead infer that the population is normally distributed. So it says to use a t-distribution, we need the sampling distribution of x bar to be approximately normal, which is why we still check the normal condition. You might see t star written as t star sub n minus 1, where the subscript represents the degrees of freedom. If your conditions are not met, so any of the conditions at all, we have to draw attention to it, which means we continue with the inference procedure, but in our conclusion, we acknowledge that the conclusions might not be reliable due to the conditions that were not met. So we state proceed with caution, and we explain why we are proceeding with caution. Okay, then it says recall significance test. So for our hypotheses, we had our null hypothesis, which is our claim, an alternative hypothesis, which is the situation we're trying to find evidence for. An example of this is null hypothesis can be mu is equal to mu naught. And then alternative hypothesis can be mu is greater than mu naught, mu is less than mu naught, and mu is not equal to mu naught. Our threshold for rejecting the null or failing to reject the null hypothesis is our significance level, and typically we use the following 3 alphas. Okay. Test statistic, we find the test statistic by seeing how far away our sample statistic is from our null hypothesis. We can use the equation statistic minus parameter divided by standard error. Remember, you won't have to use that because you have Desmos. P-value is calculated from the test statistic. When our p-value is less than alpha, we reject the null hypothesis. And when our p-value is greater than alpha, we fail to reject the null hypothesis. Okay. Our alternative hypotheses looks like the following on a distribution. So I'm going to go ahead and draw a curve for each of these. Okay. And then I'm going to write negative t star, positive t star on each of them. So remember, if we have our alternative hypothesis where mu is less than mu naught, that means we are looking at the area to the left of negative t star, and remember that area represents the probability or the p-value. Okay. If mu is greater than mu naught, then we look on the right side of the positive t star value, and again, this is the p-value. And then if mu is not equal to mu naught, then we look at both sides. So not only the left, but also the right. And that combined information is the p-value. Okay. Conducting a significant test for mean. So it says when conditions are met, the test statistic for a one sample t-test for a mean is the following. So t is equal to x bar minus mu naught over s divided by the square root of n, where t has n minus 1 degrees of freedom, X bar and S come from our sample data, and because of that, that's why we use S divided by the square root of n to represent the standard error. If you know sigma, which remember we rarely do, we would perform a one sample z-test for means, and then the formula would look like the following. Okay. Once we have our test statistic, then we can find our p-value. And remember, on Desmos, that is under the t-test formula in inference, and you type in the information needed, and then for p-value, you would go under significance test. Okay, then our conditions, so random, independent, and normal. So for random, we have to prove that we have a random sample or a random assignment. For independence, we check the 10% condition, which states that the sample size has to be less than or equal to 10% of the population size. Remember, we do not check independence when we are doing an experiment. And then for normality, we use the central limit theorem that states that n is greater than or equal to 30, then it's approximately normal. However, if n is less than 30, we either look at the problem and see if it states if the population is approximately distributed, approximately normally distributed, or, and this is the most likely one, we're going to have to graph, so we'll graph a histogram, and then we'll make sure that there's no outliers or extreme skewness. So let's look at an example. Okay, so in this example, this is a one sample t-test for a mean. It says your AP statistic teacher believes that the average number of minutes their students spend on homework every night is greater than 35 minutes. She randomly selects a sample of 10 students and records the number of minutes they spent on homework last night, and the data is written below. It says, is there convincing evidence at the 10% significance level of your teacher's beliefs? So setting up our 4 C's. First, we do communicate. And since we're dealing with means, we have to establish our parameter mu. So mu is the average number of minutes a student spends on their stats homework. Okay. Since it tells us this is a 10% significance level, we know that we are using a significance test, so we need our hypotheses. Okay, remember it stated that the teacher believes that students are spending more than 35 minutes. So that means our initial claim is that students are spending exactly 35 minutes. And then our alternative is that the teacher believes they spend more than 35 minutes. Our alpha is 0.10 since it's a 10% significance level. Our n or sample size is 10. Our degrees of freedom is 10 minus 1, which is 9. And then our x bar and our standard deviation has to be found on Desmos. So once you type in your list of the data above, you would find the mean, which you get 42, and the sample size, the standard deviation, 11.508. Okay, so showing you that here, let me open up Desmos. Okay, so I'm going to create a list. So I'm going to say L is equal to, and then I'm going to type in all the numbers on my problem. So 32, 28, 48, 33, 34, 59, 62, 45, 38, and 41. I should have 10 elements in that list. To find my mean, I would go to Functions, click on Mean, and type in L. So that's how I got my X-bar value of 42. For standard deviation, I would go to Functions, click on Standard Deviation, put in my list L, and that's how I got 11.508. Okay, so going back to my notes here. Now I'm going to move on to my conditions. Okay, so on conditions, I'm still proving random, independent, and normal. So for random, in the problem it says that the sample was randomly selected. Okay, for independence, I have the sample size of 10 is less than or equal to 10% of all students or all statistics students, which is a reasonable assumption. And then for normal, remember, I am always trying to use the central limit theorem. However, since n equal to 10 is less than 30, we have to graph. Okay, and again, what we're graphing is a histogram. Okay, so I go back here. I go here, I type in functions, I go to histogram, I type in my list, which is L, make sure that my bar height is on count and my bin alignment is to the left, and then I have to find what my bin width is going to be. In order to do that, I use the formula range divided by the square root of n. So my range is my largest number, so in this case is 62, minus my smallest number, which is 28. Divide that by the square root of 10, and I get 10.75. So I'm going to try a bin width of 10 and recenter it. Okay, I got 5 nicely drawn bins there. And then I'm going to try 11. And notice I only have 4, so 10 is going to be the best sample size, or sorry, bin width, the best bin width. Okay, so then I'm going to take this and I'm going to draw this on my conditions, because in order to prove normality, I got to show that graph. Okay, and I'm going to make sure I label everything. So I have my frequency, I have my minutes of how long these students are spending on their homework, and I'm going to label this 1, 2, 3, 4, and then 20, 40, 60, 80. Okay, so I have 1, 2, 3, 4, 5. And then here I'm going to say that I'm checking to see if there's any outliers or strong skewness. So I'm going to say there are no outliers. I know that because there's not any large gaps in my data, and no extreme skewness. Okay, which proves normality, so I can move on to the calculate portion. Okay. So calculate. So remember, I name my inference. This is a one sample t-test for means. Okay. I go to Desmos to calculate that. On a new line, I go to add inference, type on t-test, put in my list that I labeled L, hit create test. I'm doing a significance test where mu is equal to 35, okay, and my alternative is greater than 35, so I'm looking to the right, okay, and that is my answers here. Okay, so I have that my t-star value is 1.924 and my p-value is 0.043. Then moving on to my conclusion, I now can compare my p-value to my alpha. So I'm going to say since my p-value equal to 0.043 is less than alpha equal to 0.1, we reject the null hypothesis. This means we have convincing evidence that the average number of minutes a student spends on homework is greater than 35 minutes. Okay. That then leads us to the last part, where it says describe the type 1 and type 2 error. Well, for a type 1 error, remember that is when we reject the null hypothesis incorrectly. So this would be us saying the average number of minutes is greater than 35 when really it isn't. So maybe the students are spending less than 35 minutes on their homework. And a type 2 error is when we fail to reject the null hypothesis incorrectly. So this is saying we don't have evidence that students spend more than 35 minutes on homework when we actually do.